So what we did in the last few lectures is to motivate the how something like an action functional originates. So what we did, just to recall, was that we said that when you combine the principles of quantum mechanics and relativity, you want to have a formalism which is capable of creating and destroying particles. Then we said let us be very upfront about it, and we wrote down an amplitude for particles to be created from a vacuum state and destroyed back into a vacuum state. This was the Schunger's approach. That introduced the source J of x. Then we could, using very general principles, write down the amplitude for the vacuum state to remain a vacuum state. And in the simplest context, we found that it is an exponential of a quadratic functional in the source J of x. Then we said what we want is the quantity which is sitting in between two J's in that expression, which was the propagator. And we had already seen that this can be obtained in terms of some infinite number of oscillators and some time-ordered products and their vacuum expectation values, etc. So in order to connect these two, we took this vacuum to vacuum amplitude in terms of the source, and we did a Fourier transform. And that Fourier transform introduced a new set of variables. Okay, we haven't even seen what they are. These are some classical functions of space and time. And we also found something like a probability functional if you interpret this vacuum to vacuum amplitude as a generating function in terms of the source. And that probability functional was an integral of some quantity over space-time. This is what we call the action. Now we are going to reverse the whole thing. We are going to start with systems where there are action functionals for these fields, and then study the classical field theory of that, and then ask, can we quantize this and obtain the same result? And as you know, the answer is that yes, you can do that. And what is more important, this provides a more economical route to the whole process. Even though the logical motivation is what I would have said, is that you need to be able to finally calculate amplitudes for different physical processes. And the fields which you introduce is a tool which will allow you to do that. Schunger would say that the sources which he introduced is an equally good tool which will produce this, and there could be other views on how you finally compute it. But by and large, the fields are the most economical and most logical way of doing this. And it also turns out that when you want to study interactions, this is the best way to proceed. And finally, you should not forget that there is at least one field we know, namely the electromagnetic field, which is honest to God field classically. And you have to quantize it in order to get the particle picture. Okay, so this is the motivation. So I want to start talking about classical field theory, which maybe will be new to many of you. So I am going to do it a bit slowly. Now the conventional way in which the textbooks do this, I am completely unhappy with. They will start talking about springs connected to balls and the balls oscillating, or matrices, and then take continuum limit, etc. You don't need any of this. Actually, classical field theory is a very logical and very simple construct, and I think this kind of an approach confuses it. So I am going to take a more economical route, and you will see how it goes. So to do that, the claim is that if you can do classical mechanics 101, you can do classical field theory. So I will review classical mechanics first, with a particular perspective, which such that it can be immediately generalized to field. So how do we do classical mechanics? You start with an action, which is a functional of q of t. I will write it once and then we will not note these things. And it is a function of the endpoints, which I will call 1 and 2, of an integral. The action is given as an integral from t1 to t2 dt of a quantity we call Lagrangian, which in turn depends on the function q of t in terms of q dot and q. Okay, so several comments. First, we are only going to study closed systems, so there is no explicit t dependence. Second, generalization to multiple degrees of freedom is very obvious. We will do it in the end, but let us just concentrate on one q for the moment. Further, the action I said is a functional of q of t. And just let us recall the definition of a functional. Functional is a rule which allows you to find a number given a function. So if I give some function q of t, then you can, and the Lagrangian, then you can integrate this quantity from t1 to t2. It will of course depend on this, and then you will get a number. That is your action. Now, here itself there is an issue in the sense that we are assuming that action is a local functional, in the sense that there is a Lagrangian integrating which you get this. You could have a more complicated structure where the functional is still a rule which gives you a number, but it is not expressible as an integral over LFT. But we will assume that everything is local, so there is something in space-time or in, at any given time, and then you integrate and you obtain this. Okay? So this is what we have. Now, when you do the integral over dt, obviously the limits are on t alone, which is t1 to t2. But we are going to do this integral, most of the time we will consider paths of a particular kind. But right now I am not assuming anything about it. I am not assuming anything about the boundary condition or equations of motion or any such thing. That is important because action functionals are capable of telling you what the boundary condition should be. Okay, you don't have to impose it by hand. Usually in classical mechanics you will start by imposing it. We don't have to do that. So let us consider the variation of this action when the functional changes by a small amount. Okay, so you are going to do the usual classical mechanics integral dt, and you have two terms, dl by dq delta q okay, dl by dq delta q plus dl by dq dot delta q dot. That I will, okay, let me first write it as delta q dot. And then let us remember the definition of delta q. A function q is changed to q of t plus a delta q of t. Delta q is the function of t. Therefore, d by dt of that and a delta commutes, and I can take that out. So this quantity I can write this quantity here can be written as, in the first step, first I will introduce a notation dl by dq dot, just for convenience I will call it p, which is just a function of q and q dot. It's just defined by this. So you have a p d by dt of delta q, which I can write as d by dt of p delta q minus p dot delta q. So you plug it in, the variation is going to become integral over dt of dl by dq, delta q is a common to that and delta q is also there, minus p dot delta q. Then I have this d by dt integrated over dt plus p delta q evaluated at the endpoints t1 and t2. So up to this point I haven't assumed anything about boundary condition. Now I want to claim that if I set delta A equals 0, I want to get a good variational principle. It should give me some kind of a equations of motion for the system. So what do you need for that? You can see that the coefficient of delta q, since delta q is sort of arbitrary, can be set to 0 to get that equation, but that will work only if this is set to 0. So that tells you that you have to consider variations where delta q is set to 0. In other words, q should be fixed at the endpoint. This may look trivial, but if you take an electromagnetic Lagrangian, which is e square minus b square, and you play the same game, it will tell you what has to be fixed at the boundary condition. At that time, it is not at all trivial. It turns out that what you have to fix at the boundaries are something like magnetic fields. Okay? So, in the procedure which I am adopting, you should be able to reproduce for any other system. You do like this, and then you have this stuff. Then you know this is going to give you the equations of motion. So, the equations of motion which emerges from this is just p dot is equal to dl by dq There is also one more result which you can obtain immediately from this. Here we are taking this action and then you are trying a variation delta q which I had kept arbitrary. Now you can do something else. You can say that, look, I am going to study this action as a function or the functional when I already substitute for q and q dot the solutions to this equation. That is, I am going to study the action after calculating the equations of motion and then solving it, finding the classical solution, so to speak, and then I can think of this action as defined with that classical solution plugged in, but treated as a function of the endpoints. Okay, here we put delta q equals 0, but let us not do that. Let us assume that there is a q which is flapping around. Then this equation, when you have already substituted the equations of motion, this term will just go to 0. So you get delta A is equal to P delta Q. Okay. This also tells you another relation that you can have dA by dQ is equal to P. So P has two ways of, there are two ways of defining P. One way is that you can take the Lagrangian and take its derivative with respect to q dot. Alternatively, you can think of it like this, but this is very subtle, so we are going to spend a little bit of time on that. What is being done here is that you had already evaluated the action on an extremum path. Without that, it doesn't make sense to calculate that derivative. So you take an extremum path and then you change the extremum path, then you will get this result. Now there is a corresponding result in terms of variation of the endpoint time. The general result for this variation of the action, when evaluated along an extremal trajectory with the endpoints change. Now we will denote the endpoints as q and t rather than as q2 and t2 and take these to be, say, 0 and 0, it doesn't really matter. And we're just going to think of it as a function of the endpoint. So I have A, which is evaluated on an extremum path, so I am calling it A classical, treated as a function of the endpoints T and Q. Okay? Then you can write a result that the delta A of this is of the form P delta Q minus H delta T, where H is another quantity which we have defined as P q dot minus L, which is of course your Hamiltonian if it is re-expressed in terms of P. Right now it is just an energy function. It's a function of Q and Q dot here. Okay? Now this is a little bit subtle. I'm sure you have done it, but let me go over it once because it has some interesting implications in field theory. Why is this H? Why is it not plus L? That is the point to understand. After all, dA by dt is just the Lagrangian. So why is it that when I do this, I end up getting a H? Where is that extra bit coming from? The extra bit comes in because time and space are treated differently. So let me try to draw a diagram for you. So let us consider, for once I will draw a picture like normal human beings with t along the x-axis, not like the way it is, and q along the y-axis. Okay? So there is some starting point which I take to be origin, it doesn't matter. And then we are going up to this point. This point is at time t. And the reason for stretching is that this is very, very important to us. There is also a horizontal axis which is completely irrelevant to us. So this is the final q and this is the final t. So I have some extremum path which goes like this. This is a classical trajectory which goes from this point to this point. Okay? Now suppose I vary q at the end point, but I don't touch t. So I am going to vary this q by some amount. So this is delta q. So I will have another extremum path. Okay? That is the important thing. When I am talking about the derivative of this with respect to the end point, you cannot keep the same path because the moment you are fooling around with the end point, the extremum path which is connecting this will not connect this by definition. So there is the path which is also changing. So how much will the action change under that change? So you do exactly the same kind of a variation. Now the final t is not touched, you get exactly up to this point. This is d by dt of p delta q integrated. This is going to be 0 because I am working on an extremal path, and this will tell me that there is a p delta q change which is coming about, and that is exactly the first term here. Very good. Now let us do the other way around. Let us take the same picture again. This is q, this is t, this is my t is equal to constant line, and there is this point on which I have a q, and instead of doing a delta q change, suppose I do a delta t change. So I move from this point to this point. This is delta t. Okay? So originally I had this trajectory. Now this is the trajectory which I have. But the trick is that we are supposed to evaluate everything at the end point at some given time t. The moment I have changed delta t, q has automatically changed. This is the subtlety. If you change delta q here, of course delta t has changed, but we don't give a damn because we are going to just work on this t is equal to constant slice. So only that contribution comes in. But now we are again going to work only on the t is equal to constant slice. But if you change this, q changes. How much does q change? This is given by this amount. And this amount is minus q dot delta t. That is, you evaluate the q dot here. I mean, it doesn't matter whether here or here because it's a first order infinitesimal. So q dot times delta t. When delta t elapses by this much, whatever is q dot times delta t, it could have traveled. It was here. It could have traveled q dot times delta t to get here. Okay? So this length is just minus q dot delta t. Therefore, now if you write down the variation for this case, the delta A is going to have two contributions. The first contribution is that you have an integration from 0 to t and you change the end point. So that is 0 to t plus delta t minus 0 to t, that is just delta t times L. So that is easy part. So you get a L delta t, which is what you would have naively guessed. Then because the extremum path has changed, you go through this entire analysis and you get a p delta q. But this delta q is this delta q here, which is minus q dot L. So you get from that p minus q dot delta t. This is going to be L minus pq dot delta t, which is minus h delta t. Okay? This is why you pick up h here and not here. So it comes because of a fair amount of non-triviality here, which I have found that even good textbooks like Lando, which is sort of my Bible, he does it so quickly that he just calculates a derivative of dA by dt and then writes it as L and then does it in another way and gets the result. But it is not very clear why that is happening. This is why it is happening. The only book which I have seen which spends time and describes it very well is Misner, Thorne and Wheeler, Gravitation, chapter 21. Okay? So this is something which is worth spending a little bit of time and understanding what is going on. Fine. Once you have got that, you also have your standard Hamilton-Jacobi equation, because once you have a Hamiltonian and you know these two relations, you can plug it in. Okay? So this is all the classical mechanics we need, and with this we can do field theory. Okay? So that is what I am going to do next. So in order to do field theory, okay, I can wipe these out, but let me make a table here. That will be useful. So this I don't want to wipe out. So to the right side of this, let us write classical mechanics here, and let us write classical field theory here. Okay, and we will compare things further. So the first thing which we want to know is you have an action, of course, and what is the dynamical variable? So the dynamical variable in classical mechanics is some QA of t. Okay, where is the A from? I did this with one Q, and I told you that if there are several degrees of freedom, you put a A here. This A stands for A is equal to 1, 2, 3 up to n. I don't want to use I because I is going to become space time index very soon. So here what will happen? You put a A here and put a A here, put a A here and put a A here, and say that there is a summation convention. That is, whenever a capital A is repeated, you have to sum over that. Okay? So all these will just go for a ride. A, and everywhere there is a summation over A if A is repeated. Okay, so I can write for all of them. So if I look at, for example, this A. In these sort of things, it will be summed over. Okay, and it will take care of itself. It's almost magical that you just have to plug it in and it's done. So I have a set of variables like this. Now, what is going to happen here? Here my dynamical variables are fields. We are going to put a on it also soon, but for the moment let me just think of one field, like we looked at just one cube. Okay, this is the independent variable. Here it depends only on t, but you can't have that in relativity, so it just depends on t and x. That is the first step. Second, we want to look at the domain over which it is integrated. Here we have integrated over dt, so integration, so to speak. Originally I had integrated over t in a range t1 less than t less than t. Correct? Again you cannot, and the measure was just dt. You cannot have here just one of them. You have to integrate all t and x. Has to be integrated. And the domain is some volume in 4-dimensional space, which is just t1 to t2, x1 to x2, y1 to y2, z1 to z2. There is nothing mysterious about it. You can think of it as a box, but of course most of the time it's more convenient to think of some nicer shape than a box. But it is just being integrated over all the variables. So the integration measure has to be Lorentz invariant, so it is d4x instead of dt. That takes care of our first line here. What we will have now is action is going to be a functional again of these kinds of functions, and the integration is going to become over d4x, L remains L, and now we have to see what L can depend on. So originally L depended on q dot and q. Of course, instead of q now we have phi. Q dot is d by dt of something, but you can't have just d by dt, so you need to have spatial derivatives and time derivatives, so you put a di of phi. Now, once we are starting with relativistic field theory, it is extremely important to have things like indices, conventions, pakka. So just to remind you, we are going to work with a signature where eta ik is 1, minus 1, minus 1, minus 1. So if I have some quantity, let us say Vi, that is defined as eta ik Vk with a summation over this, which means that the time component will remain the same, spatial components will flip sign. Okay. So that will go for everything, and then you have an upper and lower indices will be summed over, etc., etc. So the field can now depend on phi and di of phi and integrated over this over some domain which we have called V. What do we want to do? We want to vary the fields. So let us see what happens. So when you vary the fields, you have a d4x here, and you have a phi, delta phi, dl with respect to, instead of this dot, you are going to have di of phi. So this is going to be di of phi. Then I am going to have delta of di of phi. I will first write it as delta of di of phi. Already notice that summation convention has come into operation. The L depends on d phi dot and gradient of phi, so to speak. So when you are doing this, you are doing dl with respect to d phi dot times delta of phi dot, dl with respect to gradient of phi times delta of gradient of phi. That is summed over because these i's are summed over. Okay? Fine. So we will define a phi, but here it is conventional to denote it by pi, and we will put an I here. This is again something which requires a little bit of getting used to. When you do d by dxi of some quantity, some function, let's say a scalar function, what you get is a vectorial object with vi at the lower end. That is, when you are differentiating, it is like dividing, think of it like that, and it will go at the lower end. Therefore, if you are dividing with something here, or differentiating like this will give you an upper index. So here you have a di of phi with respect to which you are differentiating, so you will get pi with an upper index, and then you have a lower index here to contract it out. So now we want to rewrite this equation. So here is your pi I. This I can write as d by di of delta phi correct? I'm just flipping these two by the same argument as before. So this is going to give me di of pi I delta phi minus di of pi I delta. I'm doing this in this way to show that you don't need springs, balls and matrices and all that. It is just classical mechanics. You just have to add an I index to that. So this is what you have got. Now let us go to the next step, just maths now. So you have d4x here. This is dl with respect to d phi because q gets replaced by phi. And this p dot is going to get replaced by di of pi I. This is delta phi plus, okay, let us do this a little bit more carefully. So what I have got is this entire term. This has been written as a total divergence here minus this quantity, right? So this total divergence is going to be integrated. Originally it was d by dt and just we integrated over dt and we got the end point. Now we have to be a little bit careful. So here you have an integral over d4x of di of pi I delta phi. Okay, so let me just write this a little nicer. di of pi I delta. Oh, let us try like this. Up to this point, as I said, has been plain sailing. Okay. Now we want to get some equations by putting delta A is equal to 0. We would like to capture this guy. So we want to know what boundary condition to put on this. Okay. You should stop me if at any stage it becomes too fast. I mean, if you're getting lost in notation or something. But as I told you, this is completely elementary common sense, nothing more than that. So you have this, and then you are going to integrate this over a volume V. Now think of this as some kind of a current again. So this is a vector with an upper index. So it is di of ji. Now we did this exactly a few days back. What did we do? We went and calculated how to do these sort of four-dimensional integrals. So let me draw a picture here again. What we did was, we said there is a time axis, this is x, this is y, and then I said let us consider a cylinder like this. So the domain of integration is inside this cylinder. So it is bounded by some T is equal to T1 here, T is equal to T2 here, and this surface is at x square plus y square is equal to r square surface. Because I have suppressed one index, if I had kept all the three spatial coefficients, it would have been x square plus y square plus z square equals r square. This is a surface of a sphere. And I would like to think of this as going to a very large distance. So it is a sphere at spatial infinity. Now when I do this integral, I am going to get the result to be, the result of this integral is integral over the boundary. So it is some d3, I'll call it sigma, which is the boundary of this V, with a normal Ni multiplying K. How do I know that? This is just Gauss theorem. If it was d3x del dot j, if you integrate, you would have said it is a two-dimensional surface integral of n dot j. Okay? Here it is exactly the same thing. It works in d dimensions, it works in Lorentzian spacetime. So that is exactly what we are doing. Gauss theorem actually is just a statement about definite integral. So if you divide it into boxes and you integrate, it just tells you that the endpoint contribution is given. So you do this. Now we want to look at what is this Nij. Now Ni's are the normals to these surfaces. There is a normal here, there is a normal here, there is a normal here on the cylindrical surface. Now the normal on this doesn't contribute because we already said that the fields there are going to die down. So I only have to evaluate these two. Okay. This is what we did long back also. So that means I am going to say that this is just going to be integral over d3x, ordinary d3x, because I am integrating on this surface. This surface is an xy plane here, and if I am doing it with three coordinates, it is x, y, z, d3x on that. And it is going to be evaluated at t is equal to t1 and t is equal to t2, and it will be subtracted one from the other of this quantity. This quantity is going to be just n dot a, and n is in the time direction, so this is j0. And j0 here is delta phi into pi 0. Now pi 0 is a nice quantity. Because we originally defined here, just as I wiped it out, just as you originally defined your standard momenta in classical mechanics, you now have di of phi. This is the definition which we used here. Generalizing P equals dl by dq dot. If I look at pi 0 is actually your old friend dl by d phi dot. This is the zeroth component of that. So this is exactly like the classical mechanics momentum. I mean, of course phi depends on space and time, but ignore its spatial dependence. Just take phi dot and compute dl by d phi dot. Whatever you would have got is like your momentum, and that is what you have here. Okay? Times delta phi. So this is just like p delta q, because this is, as I have showed you, this is just p. Therefore, the boundary condition we will put is delta phi is equal to 0. So you are going to fix your fields at t is equal to t1 and t is equal to t2. The only difference is, originally you just fixed it at two endpoints, so it was just a value. But now you have to fix your entire function. That is, you have to tell me what is the boundary functional value. So that is the next thing, the boundary condition. The boundary condition here is that q at t2 is q2, q at t1 is t1, so let me call this tj is qj. Okay? But here what you are going to do is that phi at t2 comma x is some function f of x. Phi at t1 comma x is some other function g of x. Here these were just numbers q1 and q2. Here these are two functions. That is because on that space things can vary. So you tell me what is the field configuration there? What is the field configuration here? That is left frozen. Then you vary your delta phi in between. keeping that frozen, so then this term vanishes. Because it vanishes, you get your field equation. What are your field equations or the equations of motion? The equations of motion here is, we wrote it down. It came from that particular quantity. We had P dot equals dl by dq. Okay. Here the equations of motion will be di of pi r is equal to dl by d phi. Is exactly the same. Here you have d0 of the p, so to speak, 0, because the p was defined by dl with respect to d of the time derivatives. So the time derivative is the zeroth component of that. The momentum which we have been fooling around with originally was just the zeroth component, and you had d0 of that zeroth component equal to something. Here you have the d0 of pi 0, then d by dx of pi x, d by dy of pi y, etc. With a flip in the sign in order to take care of that. So these field equations are identical to classical mechanics field equations. It need not scare you any more than classical mechanics scares you. So it is just that there are some extra indices going on, but other than that, it is identical. So what have we got here? We have got up to this pi naught and this. Fine. Now let us proceed further. Let us see whether we can get anything non-trivial. So I had a definition for the Hamiltonian. So what was the definition for the Hamiltonian originally? In classical mechanics I had, or I can write it down here. Let us see. Okay, a boundary condition I have done here. So Hamiltonian was H was PQ dot minus F. Okay. Now we want something similar. So what does H generalize? Okay, we know what P is going to become. P is going to become pi I, right? So the Q dot is going to become derivative of, because I can't just have derivative with respect to time, it has to be derivative of the field phi, right? So you immediately realize that it has to have two indices, because I cannot have just pi I and just the same index. So a generic way of generalizing this Hamiltonian is to an object which I will call T.A.B with two indices, defined by this P is going to become pi A, then this Q dot is going to become dB of phi, minus the Lagrangian. Think of it as a matrix, so the Lagrangian comes with a unit matrix. Okay. So this is the first non-trivial thing which you come across in field theory. Everything else so far has been just window dressing. So what is this object? So this object first of all carries two indices, one up and one down index, and it comes from the derivative of this phi as well as the pi, and then the Lagrangian goes for a right. So we can try to compute various components of that. For example, suppose I look at the 0, 0 component of that. Then I would have got pi 0 here, which we know already is like P. There is a D0 here, which is like Q dot. So it is PQ dot. This is 1. So PQ dot minus F. So your T00 is going to give you the Hamiltonian. That is, your H actually is going to be equal to your object T00. That is nice, but I cannot have just a 0, hanging around, because that will break Lorentz invariance. This is exactly the same old story that you cannot just have energy. You need energy and momentum. Okay? So normally if you are thinking of a point particle or some such thing, you will say that I have energy and I have momentum, and together it forms a 4-vector Pi. Unfortunately or fortunately, here we are looking at things which are densitized, so that things are dependent on space. Therefore, you cannot just, the integrated values will still give you energy or momentum, but the local quantities, suppose you want to have a 4 momentum. You had energy and momentum in a classical system, I mean in a non-relativistic system. They combine together to form a 4 vector, which I would have called PA. Now the PA for a particle is just located at some point. But PA for a field will involve an integration over space of some quantity, right? Therefore, the PA should have one more index, so that when you are integrating with two indices with an integration over some normal surface will give you a single index out. That is why these objects have two indices. Its integrals over some surfaces will give you the standard momentum. Is that clear? Yeah. Can I explain it again? Okay. So let us get the motivation right. First, there is this PQ dot minus L which I want to generalize. So if you want to generalize that, the P goes to, let us say, pi A. Okay, that is what we saw. Right? The pi 0 was just dl by d phi dot, which is just your P. So you need all the indices hanging around in order to maintain Lorentz invariance. Similarly, your Q dot here goes to d, let us say dB of phi. Because Q dot is d by dt, I can't have just time derivative, so I need time and space derivatives. Therefore, the PQ dot has to be replaced by something like pi a dB of phi. Then you want the L, so it is L, which is treated as a unit matrix. This is the quantity you are defining as T. Okay? Now what it is physically, I told you that if I take the 0, 0 component, I get just the energy density. The H here would have been the total energy in the classical mechanics. Here it will be the energy per unit volume. If you integrate it over all space, you will get the total energy. Because everything is being done as a densitized thing. In fact, in some old-fashioned textbook, they would have written this action as integral dt, then an integral over d3x of some quantity. They would have called that Lagrangian density and then integrated over d3x to get Lagrangian. That is doing horror to space-time, separating it into space and time and talking of time separately and space separately. I don't want to do that. But if the maths will take care of itself. It is just whether it looks ugly or nice, that is all. So in the same sort of way, you can think of this Hamiltonian as coming from a Hamiltonian density integrated over space. That is perfectly fine. So this T00 is what I would have called the Hamiltonian density. It gives you the energy per unit volume in space. Okay. Now we want to know what the other components are. That is not easy to get until you know the system. Okay. But I can give you a qualitative idea as to where it comes from. And later on when we are looking at system, for example, if you do the same thing for electromagnetism, in electromagnetism we have to do a little bit more gimmicks, but that we will do when we come to that. Once you do that, you get a TAB, and that TAB will have T00 components which will turn out to be E square plus B square over 8 pi, which is the energy density, or some epsilon naught if you are MKS guys. Okay, and then if you look at the T alpha 0 component, so this is energy density, then you can have components like, let us say, T alpha 0. They will essentially correspond to the alpha component. Remember that in my notation, Greek letters go 1, 2, 3, English letters go 0, 1, 2, 3. So the alpha goes 1, 2, 3. So this is a vector. And you will find it is E cross B's alpha component. That is the momentum density in electromagnetism. Okay. Then what is T alpha beta? T alpha beta actually gives you pressure. In a way, if you take a surface with a normal in the direction of n beta and you multiply T alpha beta with n beta, it will give you the force acting in the alpha direction. That is, you take a sheet of paper and there is an energy momentum tensor here. The normal to that sheet of paper is in some direction and you want to know what is the force which is acting on that sheet of paper in some other direction. Okay, and that can be expressed in terms of T alpha beta. If it is sort of diagonal, then you know that the forces are normal to that, which is what will happen with normal fluids and things like that. So the definitions of these things, as I said, only when you know the system, you will be able to figure it out. There is also one complication here, which is why I said that in general you have to be a bit careful. There is no guarantee that this quantity is symmetric. That is, if I lower this A down here as pi A dB, then I get a TAB. It is not guaranteed that pi TAB will be equal to TBA. Now, there is a requirement that the physical energy momentum tensor of a system has to be symmetric if angular momentum has to be conserved. Okay. Now, I won't go into that because we don't need this in any of our requirements, but this happens to be true. However, there is a way of, in most of the physical system, if it is not symmetric, there is a way of modifying it in such a way without creating any problems anywhere else, thereby making it symmetric. Okay, so that we will come to. Electromagnetism is one example where we will have to do that. We will do that at that time. But other cases like scalar fields, which we will discuss, it will automatically turn out to be symmetric, so we don't have to worry about it. Okay. Now I kept saying this is energy momentum tensor, but energy and momentum are supposed to be conserved, right? So is this quantity conserved? So if I look at the Hamiltonian, which is P q dot minus L, you can trivially show that dH by dt is 0. You can work that out. It's a classical mechanics exercise. So what is the corresponding thing here? So in order to look at the corresponding thing here, we are going to calculate the derivative of that. If it has been h, I would have done dH by dt, but it's a 2 index symbol, so I have to take the derivative with respect to all the power. So let us compute a quantity dA of TAB, and let us see what this is. So you have this, and I am going to compute this. So you take the dA of that. So you will find dA of pi A into dB of phi. I am differentiating this expression with respect to dA. So by chain rule, so dA of pi A times dB plus pi A dA dB of phi. Then I have to differentiate this. So that is going to be minus delta AB dA of L. L has no explicit dependence on the coordinate. It depends on coordinates only through the fields. So you have to do dL by d phi dA of phi, because we are differentiating with respect to A index. Then you have to do dL with respect to d, let us say dC of phi dA of dC of phi. Let us make sure you understand that. What you have done is to take this expression and computed dA of that quantity. Okay? So dA of this, first in this I will have a dA of pi A times this quantity. Then I will have pi A going for a right derivative of this, which is dA of dB, minus delta AB, then the derivative of the Lagrangian. So I want to compute dA of L. So that is dL with respect to d phi into derivative of phi, dL with respect to some derivative of phi, which is, I take it as dC, then that derivative of that dC of phi. Once again, one of the important things about the summation convention is that when the C is summed over, it's a dummy index. I can call it C, I can call it J, I can call it K, whatever, but this is what it is. Fine. What is this quantity? This is just pi C. Okay? So I have a delta AB hitting this. So the delta AB on this is going to give me, okay, this is pi C. If I take this inside, dB dC of phi, because there is a delta AB going to hit this dA, that is going to make it dB. Then I have this pi C and a dC, right? Now I note the fact that C is a dummy index, therefore I would have replaced it by A. This is what this term is going to be with an extra minus sign coming from this minus sign. But that is exactly this term, because dA dB is same as dB dA. So I can cancel this term with this term. Okay? Now what is left has a dA of phi here, again hit with this delta, so that becomes dB of phi. But that is exactly what I have here. Therefore, this is equal to dV of phi times dA of pi A coming from this minus dl by d phi. But that is very nice because this is the quantity which is a complicated way of writing zero. Because when the equations of motion are satisfied, that is equal to this. Therefore, this vanishes. And this is zero. So let us see what all has gone in crucially here. First, when we did this derivative, we assumed that L has no explicit dependence on xi. So a more sophisticated way, you would have said L is translationally invariant. So the translational symmetry that if I go xi to xi plus ai would correspond to t going to t plus something and xyz going to x plus yz to by a vector. So in the conventional non-relativistic mechanics, we will treat this separately. The time translation invariance of a Lagrangian will give you energy conservation. The Hamiltonian will get conserved out of it. The spatial translation invariance will give you the conservation of the spatial moment. In relativity, together you have an xi going to xi plus ai, and that will give you the conservation of some 4 momenta. But in a local version of that would be the conservation of that energy momentum density. And that is precisely what you have. This is a conservation term. So the first assumption we made was that this particular thing, the Lagrangian did not have explicit xi. That was important. The second assumption which we made is that the equations of motion hold. The energy and momentum are conserved here only when the equations of motion hold. I mean, that is of course gone in crucial. In fact, this is equivalent to equations of motion and vice versa for most systems. Most of the normal kind of systems, if you assume conservation law for the energy of momentum, you will get the equations of motion, and if you assume equations of motion, you can get the conservation law. Okay? So this is what we have. Now, why do I call it a conservation law? That is because if I just expand it out, okay, let us spend a moment on that. It is essentially this. If I had something like this, and if I had di of j equals 0, I had already shown you previously that when you integrate and if things vanish at the spatial surface, then the integral of j0 here and the integral of j0 here will take care of everything which you want. So you can do exactly the same thing here. You can take this and you integrate it over here 4 volume. The index b goes for a ride, in special relativity at least. Things get complicated if you use curvilinear coordinates or in curved space-time. But in standard Cartesian coordinates in special relativity, b will go for a ride. So you have a dA of this quantity integrated over a volume. That will give you a normal dotted with it. So you will end up getting a quantity. I don't have space here. I will write these. Let me use this part. Okay. What you will get here is that you are thinking of an integration of 0 equals integral over d4x of dA of TAB. Let me write the index b just for convenience. So I have something like this. Okay? This quantity is 0 and I'm integrating this over some surface, some region, which will give you a boundary contribution, which is integral over some d3, some coordinate sigma on that boundary, delta v, times some normal Na on TAB. Now we again use the same kind of boundary structure. Assume that things are all going to vanish at spatial infinity. Then the only contributions which I am going to get out of this is an integral again over T1 and T2, one subtracted from the other, of d3x of T0b. So the integral over d3x of t0b is like the 4 momentum. Remember, there is b is a 4-dimensional index. If b has been 0, it is an integral over d3x of t00, that would have given you the energy. If it is alpha, it would have given you the 3-dimensional vector. So this is some quantity which I could have called Pb evaluated between T1 and T2. Because it is conserved, it is independent of T, and it is of course integrated over spatial x at the two boundary, so it is just a number. You can calculate the total momentum of the system. So you find that the extra bit which we have got in terms of the Hamiltonian is exactly giving you what you need here. Fine. Now the variation of the action which I wrote down, when the endpoints are varied, also takes care of itself. For example, when we calculated the delta A for the field, you had the equations of motion term, then you had this integral over d4x of di of pi I delta phi. Then we said that we are only going to take contributions at the two surfaces, the same analysis as before, and we end up getting integral T1 and T2 d3x of pi 0 delta phi. Now what does this mean? We have seen this somewhere else, if you recall. This is, think of delta A, this delta phi. This is our definition of functional derivative. You remember when we did functional derivative, I said that if you can write it like this, then this quantity which is in between gives you the functional derivative. Therefore, the functional derivative of delta A with respect to delta phi at some spatial coordinate x, because this is all at some t is equal to constant surface, gives you this pi. This is the generalization of, okay, so let me write it down here. The, what do I write? This will be the, okay, Hamilton-Jacobi kind of relation. So here what we have got, this I don't know. Let me write this PAB, pi A dB of phi minus delta AB of L. So here what we had in this case, well, the momentum P was dA by dQ at the end point. Here what you get is that the pi naught is going to be functional derivative of A with respect to the field phi at the end points. Okay. But a more proper way of thinking about this is of course this. That is why I wrote down that relationship just to guide you through as delta A equals P delta X minus H delta T. Okay. So as far as this is concerned, we are at a constant T surface. Now you can ask what happens if I change T also. Exactly the same idea will work and you will get H delta T. But H now will be T00. So you will have an integral over d3x of T00 delta T. But you can now play an interesting game. I mean, this is something which Tomonaga did. Tomonaga was one of the three people who invented quantum electrodynamics along with Schwinger and Feynman. So the delta T, when you normally do delta T in classical mechanics, there is only a Q and T, and then you just have to do delta T. But now you have X, Y, Z and T. So you can take this surface and you can say that my delta T is by some amount here and it is by some other amount here, it is by some amount here, kind of a thing. So the delta t can be a function of where on x you are looking at. So you can essentially distort this surface to some other surface. And then you can ask, if I do that distortion, what do I get inside? That delta t can be thought of as something like a functional on that x, and that functional derivative will give you t0. I'll try to throw this in as an exercise because we are not going to need it at all, but it's a nice way to think about this. If you have come up to this, it would be a nice thing to ask, what happens to Hamilton-Jacobi equation? So you have this very beautiful dA by dt plus h of dA by dq q equals 0. And this is one of the unexplored territories in field theory. The use of Hamilton-Jacobi equation in classical mechanics is rampant, and in fact is the fastest way to solve things in many of the problems, most economical way of doing this. But in field theory it is very underused for various reasons, but I personally believe that there is something to be done here. So if any of you are interested, that is something to look at. What happens to Hamilton-Jacobi equation and what happens to later on to Schrodinger equation, which we will derive for the fields, etc. So that is some worthwhile thing, but again, since we are not going to need it, I am not going to go into that. So that is basically all that I wanted to do as far as the field is concerned. Now comes the question. This is all with one field phi. What if there are several fields? Play the same game. You add a A. Okay? So you put a here, and this picks up an A. This is A, this is A, this is A. The field equations carry an A index here. So let us just spend a little bit of moment on this. The A labels the field. Suppose you have 23 scalar field, then A goes 1 to 23. I is your space-time index. So for each one of them you do that. This is just like classical mechanics with a Qi, where this I is how many degrees of freedom you are talking about, and then time and space remain the same. So that is all you do. And this TAB, you put a A here and you put a A here. Now this is very nice. This A gets summed. Okay? So you have to get calculated for each one of them and add them up. Everything else goes further. Now what is this A? Well, as I said, I can have three scalar fields which are interacting with each other. On the other hand, I can have an electromagnetic field with a vector potential Aj. Then this field phi I can think of as A0, A1, A2, A3, and this index A can be just a space-time index. So we have at one stroke, we have done classical field theory of scalars, vectors, tensors, anything you have. In fact, even spinors can be handled, but it is a little tricky because of anti-commutator, etc. But any bosonic field is handled at one go. This phi A takes care of it. You just put multiple indices for that and you sum over that. Okay? So there is nothing non-trivial. So the one last thing which I wanted to do, now that I have introduced the multiple fields, is the symmetry transformations among the fields. This is again very simple. There are formal ways of doing this, and it is called Noether's theorem and all that, but we don't need to be that formal. What is said is that there is a transformation of the set of fields phi A. You change phi A to phi A plus some delta phi A. And you find that your Lagrangian doesn't change. Okay? Suppose it just happens that when you do this, it doesn't change or the action doesn't change. Now we want to know what is the change in the Lagrangian under this transformation. That we know because it is dl by d phi A delta phi A. See, here we need multiple fields. If you have a single field and you change it by some amount and Lagrangian doesn't change, I mean then Lagrangian is a constant. That is not what we are. So you do need more than one field. This plus dl with respect to di of that phi A. Now I can write it as just pi I of A. Then di of that delta phi A. Capital A's are summed irrespective of their position, whether it is lower or upper. Okay. Now this we write as di of pi I A delta phi A, then you subtract out minus di of pi I of A delta phi. So you write it like this and then combine this and this, thereby getting a 0. Because when equations of motion are satisfied, this is going to vanish. So when equations of motion are satisfied, this is under equations of motion holding condition, you get this to be di of pi I A delta phi. Just for fancy, I'll put A on top. So the Lagrangian changes by this divergence, okay? But we said that the Lagrangian does not change. Therefore, this is equal to 0. So you get a nice conservation law. If there is a symmetry like this, that tells you that there is a conserved current di of Ji equal to 0, where Ji is essentially proportional to, I will write it as equal to, but most of the time in physics, when you are using this, it is conventional to multiply this by some factor or divide by some factor. I mean, just to give it a physical meaning. Okay? So what is happening is that the moment you know this, all that you need to know is what is delta phi. The moment you know delta phi A, you know the theory gives you what the momentum is. You multiply by this and remember the sum over all A, that quantity will be conserved. In particular, the zeroth component of that, when integrated over space, will give you the conserved charge. Okay. So this is the simplest example of Noether's theorem. And there are more sophisticated examples. I derived here the TAB conservation by explicitly differentiating. Then I derived this by using a symmetry. In principle, you could have combined both. You could have said Xa going to Xa plus some epsilon A is a transformation in space-time, and you could have simultaneously changed the fields to phi A plus p phi A, and then if you work it out, you will get some somewhat more complicated expression, but essentially it will boil down to conservation of the energy momentum tensor, and any internal symmetries which you have for the phi will give you a conservation. This turns out to be extremely powerful. Don't be fooled by its simplicity of the derivation in 3 lines. For example, the electromagnetic current is conserved because the complex scalar fields has an extra symmetry. Okay, and same sort of thing can be said about most of the internal charges which you come across in your field theory, etc. So whenever there is a symmetry transformation of this kind, you will get a conservation law, and that is something which we will use. I think this is a good place to stop, and next week we will start doing the examples of real scalar field, complex scalar field, and electromagnetic field at the classical level, finish it off, and then we will take up the quantization of all these fields. That is the way we will do. Questions? Yeah.
While evaluating the integral
Right.
for that cylinder,
Right.
You fix the boundary at
Correct.
at T1 and T2.
Right.
Okay. What if my spatial volume is also finite? Do I need additional boundary condition?
Yes, you do. Because if you are going to deal with a spatial volume which is finite and you want your field equations to come from the result, then when you are doing this, all that you get is something like this di of, what did I write here? Yeah, di of this. This is what you get in the variation of principles. And you are integrating it over before x. Then you get 2 components on the top and the bottom. Then you get a contribution from the surface. You have to make sure that that also vanishes. It can vanish because of some special symmetries. For example, if you have a system where the pi I in those points are orthogonal to the normal. See, when you write it as an integral over surface, this index I will be hit with a ni. Okay? If you are only considering field configurations where pi i's flow along this direction, then you can have a pi I ni equal to 0. But those are again special field configuration. Alternatively, you have to put delta phi equals 0 at everywhere on the boundary. That is the safest procedure. Anything else? Yeah.
Just to comment, if you will, because this, I mean, our NST voice and
Right.
curl, okay,
Ah.
will be recognized as a continuity equation, of course.
Absolutely. Absolutely.
And if you include sources, this will just go away,
Yeah. Right.
And you will be doing that later.
Yeah, I will be doing sources, but most of the time I will think of the source as making a completely closed system.
Yeah.
And then I will take away part of it.
Then if you have that,
Correct,
fine,
correct.
yeah, okay.
You will have the full conservation and part of it will come as a
Yeah,
source.
exactly, that's what I wanted.
That is that. Yeah. So it is just continuity. A di of ji is a continuity equation. Equal to 0 is the continuity equation. Which you would have done in electrodynamics in at no end. Yeah.
Okay. I just wanted to ask, so is there any general reason why we always consider situations where we have second order equations of motion so that Lagrangian depends only upon first derivatives?
Nobody knows. It seems to work. Okay. See, for example, if you think of effective field theories like elasticity, the equations of motion are not second order. Right? If you start with a cantilever oscillating or some such thing, and if you actually do elastic vibrations, etc., you can get higher order equation. There are several places in hydrodynamics or in elasticity where the equations of motion are higher than second order. But why fundamental laws of physics are second order in time? Okay. Once it is second order in time, it is second order in space comes from sort of Lorentz invariance in some most of the contexts. So why it is second order in time? That is some field configuration in its first derivative, if it is given, everything else is fixed for you. Is I don't know of any fundamental reason why it works, but it seems to work.
One more thing, like, integral L before x. I mean,
Yes.
We use the script stylized L, but that's Lagrangian density.
Yeah.
Is totally an invariant, but h before x is not, because Hamiltonian is zero complex.
Correct. In fact, that is why I only use L.
Yeah, exactly.
For
So-
H for me is T00.
Yes, exactly. So that is a better,
Absolutely.
Like,
That is exactly what happens when you commit this murderous thing of separating space and time. And you find that the Lagrangians are genuine scalars and can be integrated over D4x. Actions are genuine chiral,
Yes.
but Hamiltonian is sort of your construct with.
tangent bundle or something
That's
like
right.
that.
So the problem is all the Hamiltonian approach to field theory suffers from it.
Yeah.
Because you have to do 3 plus 1 and I don't like it. So I will not ever touch it.
Very unified and
Absolutely.
holistic approach.
It's a holistic approach to the whole thing.
Amazing.
Yeah.
Fantastic.
Right.
Sir,
Yeah.
basically, you said that this transformation del A TAB
Right.
equal to 0, it is equivalent to equations of motion for most systems.
Yes.
So, like,
Yeah.
in
When it is not.
when is
Okay,
it?
these are really exceptional cases. What happens, for example, even in electrodynamics or some generalizations of electrodynamics, when you write this, here it will not be a single simple function. Okay, there will be some integers here because phi a will come in now. So if there are multiple fields, there will be a phi a here, and this whole thing will have an index a. Now that a can have, for example, 2-index structure. If it is a 2-index structure, then the contraction of this 2-index onto this 2-index is 0 is what you get. Then you have to assume that the determinant of this is non-zero in order to get this to be 0. So there are some integrability conditions which comes about by going to this equal to 0. Up to this you will get. Then you have to say that I can take the thing which is in the curly bracket to be 0. And if there is in this particular case it is trivial. But if there are multiple fields, suppose I have a here and a here. All that you know is summed over all that a, it is going to vanish. But you have to say for individually for each one of them it is 0. Right? So there are cases like that, but these are more exceptions than rules. Most of the time, energy moment conservation will imply field equation and vice versa. Yeah.
Actually, it's divergence free only on the A index. If I take B, if it's not symmetric,
Yes.
then necessarily it won't
Yes,
be easy.
that is exactly why angular momentum will not be conserved. Okay, so it will run into serious trouble. So we will not ever study energy momentum tensors which are not symmetric. So in this particular case, I didn't need to use that, but we will at some stage go and assume that you have done something by adding a term whose divergence is irrelevant. such that it is made symmetric, which you can always do. It's something called Belinfante is the, I think is the name which goes with it. Okay, though I haven't historically looked up who first did that.
But why can't we just symmetrize it at this level? Is it incorrect?
That will not work. That is incorrect. It does not work even in electromagnetism.
What will happen? Lorentz covariance will go up higher, and if you
No, Lorentz covariance, conservation will go.
Yeah, conservation will go. Yeah.
Lorentz covariance will be maintained, but conservation will go. So you need to add to it the divergence of a third rank tensor such that all other things are preserved and the thing becomes symmetric. In electromagnetism, it can be done by inspection. I mean, when you see it, you know what to add, and then you can take care of it. We will do it when we come to electromagnetism.
But a general procedure for any.
Oh, general procedure is very, very trivial. You write down the Lagrangian in curvilinear coordinates, vary it with respect to the metric, and you will get a symmetric conserved energy momentum tensor. So, because after all, what is energy momentum tensor? Energy momentum tensor is that which produces gravity. Therefore, if you are talking about energy momentum tensor without bringing in gravity, you will get into nonsense. So, you have to talk in terms of something like gravity, but you don't need gravity. You just write down the Lagrangian in a generally covariant way in curvilinear coordinates and cheat a little bit and just vary GAB arbitrarily. Because if you start with a GAB in a curvilinear coordinates and you vary GAB arbitrarily, you will not get to another curvilinear coordinate thing. You will get to a curved space-time. But you vary it formally with respect to that GAB, and what you get is your TAB. That will be symmetric and it will be conserved.
And the interpretation of components of this most general energy momentum tensor is still the same, that the space-space component will be the mechanical stress.
You mean when I do it with the general relativity?
Yeah.
Oh yeah, in general relativity it is more obvious. Because you can think of that delta GAB and study delta GAB arising out of coordinate shifts. And then you can interpret that one of them is momentum and the other is energy density. You can actually do that. Yeah, the interpretation remains the same. That is the answer.
So basically what I wanted to ask is, if I have field configurations in this case, for instance, which give you something like P equal to -3 or something like that.
Yes.
So it is the actual
Absolutely.
Mechanical pressure
Absolutely.
which is negative.
Absolutely, yeah. In the sense that if I put a sheet of paper, it has to do something to it as though it is a negative pressure. That is why the universe with normal matter does behave as though it has a negative pressure and it accelerates. I mean, it only cares for the TAB structure. What you call pressure is some kind of a normal force on some surface. So you give me one normal and you give me a TAB, I will give you the force in some direction. And that is a general prescription. Any other comments? Okay.